I think you all know Bruce Kleiner and John Lott played a very important role in the verification of Gregory Perelman's work on the Poincare conjecture, because very early on they started writing a set of notes, actually an exegesis of Perelman's work, sort of line by line explanations, clarifications, filling in of details of his arguments. They posted these on the internet. They were revised from time to time. Eventually they were submitted to archive and to, let's say, topology and geometry, topology and geometry, where it appeared as a refereed article, modestly entitled Notes on Perelman's Work. So without further ado, I introduce Bruce Kleiner.
Well, of course, it's a great honor to be speaking here. I guess I have a hard act to follow. My perspective is going to be rather different from that of the last talk, which was very large scale. It's going to be more microscopic. So specifically, I'm talking about the role of collapsing in Perelman's work. And so this, before I start, so convention, manifolds are going to be orientable without further mention. And so let me begin by just very briefly saying where collapsing arises in his proof. And in a short time, I'll define collapsing and discuss other background, just to give a snapshot of this. So let's recall that Perelman's proof begins with some closed three-manifold M0 and an arbitrary metric, G0. And then what he does is he runs Richie flow, starting with this metric. And when singularities form, he stops the Richie flow, performs a cut and paste argument, or a construction, or surgery. And then that gives him a new smooth manifold. He restarts the Richie flow, and then continues that until singularities form, and so on. So this is the Richie flow with surgery process, and it gives you a one-parameter family of Romanian metrics. And so the collapsing shows up in two different ways here. First, it shows up in the finite time analysis. So in order to even justify or construct this Richie flow with surgery to show that it's well-defined for all time, it's necessary to understand the structure of singularities. And to do this, well, one of the key ingredients was a non-collapsing argument. So this is relevant in just understanding the structure of singularities. And then the second place collapsing appears is in studying the large time behavior. So here you want to determine the topological structure of this manifold MT when T is large. So the second place is going to be the main focus of the lecture, although I'll say a little bit more about the first one later on. Okay, so before I get to this, I need a definition. So a graph manifold is an orientable three-manifold, maybe with boundary, with the property that you can find a finite disjoint collection of embedded tori, such that when you remove these tori from the manifold, what's left has connected components, and each of them is a circle bundle over a surface. Okay? So the simplest example would just be a circle bundle, but more generally, you get a graph manifold by taking a bunch of circle bundles over compact surfaces with boundary, and then you consider boundary components of these pieces, which are tori, and you glue them in pairs. That's how you get a general graph manifold. All right, so now let's return to the Richie flow with surgery. So we have the metric GT. What I'll do is rescale that by the metric tensor by 1 over t to define the metric g hat of t. And so the distances of this will be scaled by 1 over root t. And Perelman shows that this manifold has a decomposition into two pieces. These are compact manifolds with boundary. So call one piece the thick part, the other the thin. So these two things meet along their common boundary. And the boundary components are incompressible tori. So these are embedded tori. Their fundamental groups inject in the fundamental group of the manifold MT. And the thick pieces, or the connected components of them, are diffeomorphic to finite volume hyperbolic manifolds. And the thin pieces, or the thin part, is a graph manifold. Right? So the point is that graph manifolds are known to have a geometric decomposition in the sense of Thurston, and so this proves the geometrization conjecture. All right? So the proof that the thick part is hyperbolic, it comes from the Richie flow argument and monotone quantities and some rigidity, but the proof that the thin part is a graph manifold is based on collapsing theory rather than Richie flow. So that's going to be the focus of the lecture. All right, so now I want to shift gears and return to some of the background, starting with convergence of Romanian manifolds. So first of all, what is CK convergence of Romanian manifolds? So this just means you have a sequence of Romanian manifolds. It converges to another Romanian manifold in the CK topology if the metric tensors converge modulo isometry. Okay, so more precisely, here's a non-negative integer. I'll just say that a sequence of Romanian manifolds converges in the CK topology if, so for large J, you can find a sequence of metrics here, Gj bar living on the limit manifold, such that the jth manifold in your sequence is isometric to the limit manifold equipped with this bar metric, Gj bar, and the bar sequence converges in the CK topology to the limit metric G infinity. Okay, so this gives a natural notion of convergence. In fact, you can cook up an associated notion of metric on the sort of CK metric on Romanian manifolds up to isometry, but that's not going to be relevant. What's really needed is just a notion of closeness or the topology. All right? So, all right, so the first fact in this setting is the compactness theorem. So give yourself some numbers di and c, and suppose you have a sequence of Romanian manifolds, mj, so that the diameters of the manifolds are uniformly bounded by some d, and each manifold has injectivity radius at least I everywhere. And finally, assume a uniform bound on the norm of the curvature tensor for every manifold in the sequence. Well, so then a subsequence of this converges in the C0 topology. Right? So one immediate corollary of this fact is that if you look at the collection of all compact manifolds which satisfy these three conditions, so manifolds whose diameters are most d, the injectivity radius is at least I, and this bound is satisfied, then there are only finitely many smooth manifolds up to diffeomorphism that show up in this class. And the reason to see this, I mean, if that weren't true, then you'd have infinitely many diffeomorphism types. So you could find a sequence of manifolds where the manifolds are pairwise non-diffeomorphic. Okay, then you apply the compactness theorem, and you conclude that all but finitely many are actually diffeomorphic to some fixed limit manifold, which is a contradiction. Okay. So in this compactness theorem, so the assumptions are all necessary. So let's look at some examples. So first of all, if you take a sequence of product tori, so a circle of length 1, product with a circle of length 1 over j, so this is a torus where one factor is shrinking down. So this satisfies the diameter bound and the curvature bound. The curvature is just 0. It's flat. But it doesn't have a convergent subsequence. You can see that, for instance, because the injectivity radius is going to 0, but also the volume is going to 0, whereas the injectivity radius and volume are continuous, easily seen to be continuous with respect to this notion of convergence. This is an example of a collapsing sequence. You can think of this torus as kind of collapsing down to a circle, corresponding to the first factor. I'll come back to that later. Another example to think about is where you drop the diameter bound. So here, then consider this sequence. Again, a product of two circles, but where where the second factor has length tending to infinity. So this, again, does not have a convergent subsequence because the diameter is tending to infinity, and if it were converged to something, then the diameter would have to converge to the diameter of the limit. But if you think about this example, so you have these tori, so in one direction the length is 1, in the other direction it's tending to infinity. If you imagine standing on the torus, then still in some sense this converges because it looks more and more like just a circle across the real line. Okay? So if you change, so you can deal with this phenomenon, you can modify the statement of the compactness theorem by considering a modified notion of convergence, a pointed convergence. So here, so I'll need this later on. So a pointed Romanian manifold is a triple MGP, where M, comma G is a Romanian manifold. P is just a choice of base point. And so I want to talk about what it means for a sequence of pointed manifolds to converge to some limit pointed manifold. And so here's the definition. So it's pretty much as before. First, so we take the sequence, converges to a pointed limit here if you can find a sequence of metrics on the limit manifold so that two things happen. First of all, the metrics converge on the limit manifold in the CK topology, just as tensor fields, on compact subsets of the limit. And also for every radius r, if you look at the r ball in the jth manifold and the r ball in the limit manifold equipped with this gj bar metric, those two balls are isometric for large j. Okay? So if you use this, if you change from manifolds to pointed manifolds and convergence to pointed convergence, then there's a version of the compactness theorem where you do not need the diameter bound. So you just need to know that if you have a sequence of pointed manifolds where you have a uniform bound on the curvature and a lower bound on injectivity radius, then the subsequence will converge in the pointed topology, point CK topology. Now there are other versions of the compactness which show up. So first of all, if you assume stronger bounds on the curvature, so if you assume that the kth covariant derivative of the curvature tensor is bounded by C in norm, where little k runs up to this number big K, so then you can strengthen the convergence conclusion, just saying that you have CK convergence instead of just C0 convergence. Also, there's a version of this compactness theorem for Richie flows, which is due to Hamilton. And this is actually a key tool in studying Richie flow, because the idea is you want to understand, so this shows up in the construction of Richie flow with surgery, you want to understand the part of the Richie flow where you have large curvature. So you take a Richie flow, you look at maybe a sequence of points now in space-time where the curvature is getting larger and larger. So as a remedy for the fact that the curvature is blowing up, you rescale, you magnify the metric, because magnification makes the curvature go down, right? So you blow up or rescale in this way, so you get a sequence where the curvature remains bounded, and you would like to claim that there's a convergent subsequence. And then you can study the properties of the limit. And so the first, Perelman's first breakthrough was what's known as his non-collapsing argument, which is a encoded way of saying that he showed that in this kind of situation of such a blow-up argument, you will always have the injectivity radius bound, the lower bound in injectivity radius that's needed to apply the compactness theorem. So therefore, you always can take the limit. And this was a major obstacle for Hamilton prior to Perelman's work. Okay? So I should just say that the injectivity radius bound in the non-collapsing argument is applicable only when you consider sequences of points in space-time where there's a uniform upper bound on the elapsed time. All right. So now I want to move toward collapsing. So here, this was first studied by Cheeger and Gromov in this form. So I'll say a sequence of Romanian manifolds collapses with a two-sided curvature bound, or it collapses in the sense of Cheeger and Gromov if two things hold. So first of all, the curvature is bounded above and below uniformly, independent of J. And secondly, the injectivity radius tends uniformly to 0. Okay? So in fact, if you consider a sequence of manifolds where the first condition holds, so you have a uniform bound on the sectional curvature, and if you assume in addition the diameter is bounded, then there's either a subsequence which converges, or there's a subsequence which collapses. So if you consider sequences of manifolds with bounded curvature and bounded diameter, then this is really sort of the opposite case, the other case, from the case of convergence. Okay? If you don't have a diameter bound, then you can have a sequence where part of the sequence it's collapsing, and other places it's converging to something. Right? In any case, this is the form of collapsing that was studied by Chico and Gromov. And let me just mention that there's another way to think about this, which is useful in transitioning to later setting in the lecture. So suppose you have a manifold with a curvature bound of C, and then this lower bound on the injectivity radius is equivalent to a lower bound on volumes of balls. Okay, so the injectivity radius at a point P will be small if and only if, when you look at the ball of radius R, that's small. Okay, so therefore you can, in this definition of collapsing, you can replace the second condition with this statement that every, let's say, unit ball, you could take some other radius, the volume of every unit ball tends to 0 as J goes to infinity. All right, so what are some examples of collapsing? Well, we already saw one a minute ago, but here's a more general version. Just take any compact Romanian manifold, look at the product of that manifold M with a circle of length 1 over J. Okay? So this, as you see, there's nothing interesting happening to the curvature. The curvature stays bounded in the sequence, but the injectivity radius degenerates to 0. More general version of this is the following. You take suppose you have a compact Romanian manifold with a circle action, a free isometric circle action. And then you can form this, you can construct the following object. You take the manifold, you cross it again with a circle of length 1 over J. Okay, it's the sequence we just saw a moment ago. So now the circle has an isometric action on M. It also has an isometric action on the circle just by left translation. So we have a diagonal action of the circle on the product, and then you can form the quotient, which inherits a natural quotient Romanian metric. And this sequence of manifolds also collapses with a two-sided curvature bound. Now, the point about this sequence is, topologically, we're first taking the product with the circle and then dividing out by the circle. So the underlying smooth manifold here is diffeomorphic to the original manifold M. So this produces a sequence of metrics on the same underlying manifold, which collapses. Now, what's relevant for the later story is that if you look in dimension 3, you look at graph manifolds. So then Chico and Gromov showed that every graph manifold collapses. So it has a sequence of metrics which collapses with a two-sided curvature bound. So remember, a graph manifold is a manifold which can be cut up along tori, so the pieces that remain are circle bundles. Okay? So it's built up of pieces of the sort that we were just considering a moment ago, the kinds of pieces which collapse. And so their construction involves showing that you can collapse each of these circle pieces in such a way that the metrics are compatible along the tori along which the pieces meet. Okay? Anyway, so more generally, they gave a characterization of collapsing in the following form. So if you have a closed manifold M, so then you can find a sequence of metrics which collapse with a two-sided curvature bound on this manifold, if and only if this manifold admits an F structure of positive rank. Okay, so I'm not going to give the definition of an F structure of positive rank, but roughly speaking, involves having a cover of the manifold by pieces, each of which has a finite cover with a torus action on it. And these structures are somehow compatible on the overlaps. Now, it follows just from the definition of F structure, which I'm not giving, that in dimension 3, if you have a sequence which collapses with a two-sided curvature bound, then it has an F. These guys have F structures for large J, and so for large J, this manifold will be a graph manifold. Okay, so collapsing a dimension a manifold collapses in dimension. Three-dimensional manifold collapses if and only if it's a graph manifold. Now, so coming back to Richie flow, so in 1999, Hamilton studied a certain class of Richie flows in dimension 3. So he was interested in studying the large time behavior of Richie flow. So what he did was to simply impose an assumption on the curvature, basically that if you take the manifold, the Richie flow, so he assumed that the Richie flow existed for all time with no singularities, and he simply assumed that if you normalize the metric at time t by to make the volume 1, then there were uniform upper and lower bounds on the curvature of the resulting metrics. So under this assumption, he was able to show that the geometrization conjecture held by invoking, in part, one of the ingredients was precisely this collapsing theory of Cheeger and Gromov. Okay? So after that, I mean, he had formulated a program for attacking the geometrization conjecture. I mean, formulated it more explicitly, and one of the steps involved proving that if you start with an arbitrary metric on a 3 manifold, and then you run Richie flow with surgery, eventually, sometime onward, there will be no more surgeries. And moreover, the condition which he imposed in the paper actually holds. So proving that the curvature bounds he hypothesized in this paper held in general. So actually, that remains an open problem today. It's one of the interesting analytical problems about Richie flow in dimension 3, whether one can prove these curvature bounds. But I think one of Perelman's key insights was a way of just dodging this problem. So he realized that you could still prove the geometrization conjecture by instead of using Cheeger-Gromov collapsing, he used a more general form of collapsing, where you have weaker curvature assumptions. So he could complete the proof under weaker curvature assumptions, and that meant the burden of proof was lighter. So he was actually able to verify the curvature conditions which are needed in collapsing. All right. So so now I want to talk about the form of collapsing that shows up. So this is collapsing with the lower curvature bound. So it's the collapsing assumptions are weaker in two different ways. So first of all, we're no longer assuming you have a sequence of manifolds with a global curvature bound, global upper and lower curvature bounds. So we're looking instead at manifolds where you have kind of a local bound on curvature. And second, instead of looking at two-sided curvature bounds, we just look at lower curvature bounds. Right? So to express this, to localize the collapsing condition, you want to first attach a scale to each point in the manifold. So, if you have a Romanian manifold and a point P, so define the curvature scale at P to be the supremum of the numbers R, so that if you look at the R ball, that has sectional curvature at least 1 over R squared. Okay? So let me unwind this a little bit. So the way I think about this is to take the R ball, and I rescale the metric on the R ball so it becomes a ball of radius 1. And then this condition on the sectional curvature of the R ball becomes a condition that the metric on the rescaled ball, the metric on the unit ball, has sectional curvature at least -1. Okay? So right. So this supremum will will be finite. I mean, it can actually be infinite, but it's infinite if and only if the manifold is a manifold with non-negative sectional curvature. Okay? So I'll denote this curvature scale by this R sub p. And now, collapsing with a lower curvature bound means the following. So let's pick some number w. And I'll say this, an n manifold is locally w collapsed with a lower curvature bound. So I'm not really sure. You could imagine scrambling the words in this condition. I'm not sure it's the right way of parsing this. Anyway, the mathematics is clear. We're saying that if you look at you take a point P and you look at the ball of radius, the curvature scale, well, then that should be at most w times its radius to the nth power. Okay? Now, if in the case when the curvature scale is infinite, then we don't impose any condition at all. So you can localize this to a subset. Let's say the manifold is locally collapsed along a subset Y if this condition holds for every point P belonging to the subset Y. Now, let's return to the setting of Ricci flow with surgery. So here's our time t manifold with the metric gt. I rescale that by 1 over t as before. So we have, as I said before, this kind of thick-thin decomposition of the time t manifold. And so, as I said, this part, one shows, becomes hyperbolic. And the other part, what Perelman shows is that the other part, for every w, this thin part is locally w collapsed to the lower curvature bound for large t. Okay? So this is a collapsed manifold. And there's a theorem which says that if you have, there's some w0, some positive number w0, so that if you have a w0 collapsed 3 manifold, then it's a graph manifold. Right? So this is the version for closed manifolds. Of course, in the setting of the geometrization conjecture, you may have boundary. There's a version for boundary, but I'm just suppressing that. Okay? So in the proof of the geometrization conjecture, you just apply this theorem to the thin part, because you know for this w0, for large t, the thin part will be w0 locally collapsed. And so it's a graph manifold. All right. So I should mention, although this theorem is true in this form without any other hypotheses, if you're interested in proving the geometrization conjecture, then you can use some additional information that's coming from the smoothing or regularizing properties of the Ricci flow. So, and because of that, again, if you're just interested in the geometrization conjecture, it suffices to prove this collapsing result under some additional bounds on the derivatives of curvature. So I'm not going to state them here, but as I go forward, there'll be a place or two where these bounds are used, and I'll just point out that here I'm using these curvature bounds. It's just a little bit technical to state them, and I don't want to spend time on that. I'm going to emphasize it's true without them. So the benefit in giving this, in using them is the proof is much simpler, at least if you sort of measure the total length in terms of journal pages, because it allows you to avoid this results about Alexandrov spaces, so Perelman's stability theorem. And you can just replace those with the smooth compactness theorem, which I mentioned earlier. Okay? So I mentioned there are versions of this local collapsing result due to Perelman, so he stated this result in his second Ricci flow preprint. And then there's a paper by Shio and Yamaguchi, which gives the version based on Perelman's stability theorem. And then the versions by Morgan Tien, Bessier, Basson, Mayoparty, Tsao and Ge, and John Lott and myself. So in the remaining time, I want to say a little bit about the proof of this collapsing result. So this is just a sketch, and I'll be following the line that, that John Lott and I use. And I want to emphasize that this really is a sketch, so many details are suppressed. Okay. So first of all, let's come back to the the assumption. So I want to look at a locally W0 collapsed 3 manifold, where I think of W0 as being small. So what does that condition really mean? Well, by definition, it means you know that if you look at a point P, you look at the ball with radius the curvature scale. So then the sectional curvature of that is at least 1 over the radius squared, and the volume is at least W0, is at most W0 times the radius cubed. Right? So now let's first try rescaling that so that the ball of radius equal the curvature scale is rescaled to a unit ball. Okay? In other words, you rescale distances by the factor 1 over the curvature scale. So this translates into the statement that the unit ball in this rescaled manifold, so this notation just means I'm rescaling distances in this Romanian manifold by that factor. Okay? So this unit ball has sectional curvature at least -1 and volume at most W0. Okay? So now with this rescaling, we see that the collapsing condition just becomes a condition where you have a uniform lower bound on sectional curvature and small volume. Okay? So it looks a bit like the global version of collapsing that I was considering earlier, except that I only have a lower bound on curvature instead of two-sided bound. Now let's consider a different scaling. So let's pick a number, some W, between this very small number W0 and C3. C3 is just the volume of the unit ball in R3. Okay? So I'll define the W volume scale at a point to be the smallest radius so that the volume of the R ball is equal to W times R cubed. Okay? So if you think about, fix a point P, and you look at the volume of the R ball divided by R cubed, all right? Now when R is very, very small, the ball is almost Euclidean. So its volume divided by R cubed is going to be close to the Euclidean value C3. Right? Now as you increase the radius, by the time the radius reaches the curvature scale, you know that that ratio, the volume divided by R cubed, has dropped down to this very small positive number W0. Okay? So somewhere in between, it's going to hit the value W. And that's, I mean, the first time it hits that will be this volume scale. Now, because at the curvature scale, the volume divided by the radius cubed is a very, very small number. If you think of this W as being large compared to W0, so think of the ratio W over W0 as being large, but also think of W as being fairly small compared to C3. So then in this case, the W volume scale, which I'll denote by this, R sub PW, this will be much smaller than the curvature scale. All right? So a minute ago, we saw if you rescale to make the curvature scale equal to 1, you see an object with lower, you see a unit ball with a lower curvature bound of -1 and small volume. Okay? Now we're going to dilate so that a much smaller scale becomes the unit scale. And so that ball, the curvature radius, will expand to something very large. And what do we see? Well, we find that the unit ball in this rescaled manifold has volume W. And what happens to the ball in the original manifold of the curvature scale? Well, that becomes this ball. And you find that very, very large ball has almost non-negative curvature, right? Because you get this by taking the unit ball, where you have a lower bound of sectional curvature is bigger than -1, and then you apply a strong dilation to that, which will bring the lower bound close to 0. All right? So the idea here is that you see at this scale, you see a very large ball which is almost non-negatively curved. So you can try to apply the theory of non-negatively curved manifolds to understand the structure of the manifold. And the other thing is that you can think of this W as a small number, but not too small. Okay? So at this scale, the manifold looks kind of collapsed, but not too collapsed. All right. So now with this kind of preview, the scheme of the proof goes as follows. So first, we're going to study the manifold at a certain scale. So it's actually not going to be a volume scale. It will be some modified version, but it's a scale much smaller than the curvature scale. And at that scale, near every point, we're going to identify some geometric structure, which will be like a fibration. And in the second step, so we'll have this structure near every point in the manifold when it's viewed at an appropriate scale. So then the next step is to see how what happens when these structures overlap at nearby points. You want to see that the structures are somehow compatible. And so once you've done that, then it becomes possible to try to glue them together. So you see local fibration structures at this small scale, but then you can piece these all together in an argument like a partition of unity argument to some kind of global fibration, okay, of certain parts of the manifold M. And then finally, after you've pieced this together, you see that the manifold can be decomposed into fibered pieces, and you just simply recognize that you have a graph manifold. Okay? So now, before I really get into the real sketch, let me just mention what the ingredients are. So first of all, the theory of non-negatively curved manifolds, which is really so the part due to Cheeger and Gromall in the 70s. Then there's the critical point theory for distance functions. So this is due to Grove and Shihama. It was further developed by others. And then we need to use Hamilton's theorem, which gives a classification of non-negatively curved three manifolds. So this is one of the consequences of his first Richie flow paper in 1982. And finally, we use compactness results of the sort that I've mentioned so far, maybe a couple of others, involving Gromov-Hausdorff convergence. So apart from this, the proof is elementary. Okay? So let me now just review a little bit about the structure of non-negatively curved manifolds. So first of all, Hamilton showed that, well, he classified these manifolds up to diffeomorphism. They all have Romanian metrics, which are isometrically covered by the three-sphere S2 cross R or R2, these three Thurston geometries with the standard metrics. So you can say more about the structure, but for the purpose of the theorem that we're trying to prove, the main point is that they're all graph manifolds. Okay? Now, what about the non-compact case? So suppose you have a complete non-negatively curved Romanian manifold. So Cheeger and Gromall showed that a complete manifold with non-negative curvature is relatively simple at infinity. At least topologically, you have a compact manifold. It's a totally geodesic submanifold S, which they call the soul. And so since it's totally geodesic and it sits in a non-negatively curved manifold, the soul is itself non-negatively curved. And then they show that this non-compact manifold X is diffeomorphic to the normal bundle of S. Okay? So to understand the topology of X, you just need to understand the normal bundle of the soul. The second fact is that non-negatively curved manifolds are asymptotically conical. So there are different ways of saying this, but let's say we fix a point P in X, then for large R, if we rescale this manifold X, so we blow down or scale down, for large R, this looks nearly conical. So what do I mean by that? Well, in a cone, a metric cone, you have a vertex, and the space is a union of rays leaving the vertex, right? So saying this is nearly conical means that for large R, if you look at the unit ball in this space, every point will lie close to a ray emanating from the base point P. Okay? So as a consequence of this conicality, you can apply this critical point theory of Grove and Shihama to see that that the R balls centered at the base point P are diffeomorphic to the whole manifold X for large R. So the point is, so of course in a Romanian manifold, if you choose a point and you look at the distance function from that point, it's not a smooth function, it's just a Lipschitz function. But nonetheless, Grove and Shihama developed a useful notion of critical points or regular points for these distance functions. And they showed sort of version of Morse lemma A, that if you have a level set where there are no critical points, then nearby level sets are diffeomorphic to it, and you have a product structure. And so in this setting, because the manifold is asymptotically conical, that implies that the distance function from the base point has no critical points far away from the base point. All the critical points lie in a compact set, which means that the end is diffeomorphic to a product. Okay. Okay. So now what happens in dimension 3? So here are the possibilities. So the soul has dimension 0. Now this is a point. So then its normal bundle is just a copy of R3, so X is R3. If the dimension of the soul is 1, since it's compact, we're looking at a circle. The normal bundle has to be trivial because we're assuming that the manifold is orientable. So you have S1 cross R2. If the soul has dimension 2, then X is diffeomorphic to the normal bundle, which is just a line bundle. So the possibilities for the soul, which is a non-negatively curved surface, are, so if it's either the two-sphere or the torus, then the line bundle is trivial. You just have a product. If the soul is RP2 or the Klein bottle, then it's a twisted line bundle. Okay? So the first thing I want to do is to identify a nice scale. So we'll attach to each point in the manifold a scale, call it R sub p, with some nice properties. So first of all, this scale will be much smaller than the curvature scale. Second, the assignment of the scale to the point defines a smooth function with Lipschitz constant lambda, which is much smaller than 1. Okay? So now if we look at any point in the manifold, we look at the ball of this radius, its volume lies between the radius cubed times W prime and W bar times the radius cubed, where here W prime and W bar are suitably chosen constants lying in this interval. So you should think of them as both being large compared to W0, but small compared to the C3, small compared to the volume Euclidean ball. So what this means is if you choose any point in the manifold, if you rescale the manifold by the scale that's attached to that point, and you look at the unit ball in the resulting rescaled object, so this has volume lying in this interval W prime, W bar. Okay? So you should think of this, again, these are numbers that are small, but not too small. So what we have is as I said earlier, in this rescaled manifold, what you'll see is a large ball which has almost non-negative curvature. Okay? And so you have something with almost non-negative curvature, and the volume of the unit ball is small, but not too small. All right? So now, so if you think about what this volume scale gives you, it means that it provides a way of sort of instructions for magnification to use as you move around the manifold. And this fact that the Lipschitz constant is small means that if you're looking at the manifold at the preside scale at a point P, and then you start, within your view, you start to move at unit speed, then, of course, the scale will begin to change. But it changes very slowly because the Lipschitz constant is small. Okay? So in this setup, we can arrange the Lipschitz constant as small as we like, which means that if you have localized constructions, it's almost as if you're in the case where you have a fixed global scale. Right? So for that reason, once you have this volume scale, the theory of local collapsing is almost the same as the theory of global collapsing, at least when you're considering local arguments. All right, so now let's fix some large integer k. So if you use the bounds on the derivatives of curvature, which I suppressed when I stated the theorem, you apply the smooth compactness, what you see is that the manifold M rescaled by this scale is close in the CK topology to a complete non-negatively curved CK smooth Romanian manifold, NP, with a base point star, okay? Because I'm talking about closeness in the pointed sense. So I'll think of this. So again, you rescale the manifold to this scale. You see something which is up to a good approximation, a non-negatively curved manifold. So what we want to do is to think of that non-negatively curved manifold as a model for the manifold M. and use that as a guide. So I'm going to classify the points according to the structure of the model manifold. So the first phase is kind of a crude stratification. So let's pick a point P and M. So I'll say it belongs to a 2-stratum. If this model manifold NP can be chosen so that it splits isometrically like this. You can write it as R2 cross some cross-section. And I say it may be chosen here because this model manifold NP is not unique. It's sort of defined up to some measure of closeness. And that measure of closeness involves a parameter. I've been suppressing parameters all along, okay? So otherwise it would be just too burdensome to follow what's going on. And then points in the 1-stratum if it doesn't belong to the 2-stratum, so there's no splitting like this. But you can split off, this NP can be chosen to split off an R factor. And then if you can't split off an R2 or a copy of R, then the point is in the 0-stratum. Okay? So let's consider the structure that is present in these different cases. So if you start with the 2-stratum point, so that this model manifold looks like this. So then, of course, NP is 3-dimensional. We have something 2-dimensional here. This is 1-dimensional. So it's a 1-dimensional manifold. And we know the unit ball in the model manifold has small volume. So it follows that this cross-section, NP prime, is actually a small circle. Okay? And so now what I want to do is, so I want to use the fact that M, with this rescaling, is close to the model manifold. So you can just transfer this projection map. So we have the model manifold R2 cross the cross-section. That projects to the R2 factor. We transfer that to M. Okay? In other words, so since this is close, that means there's a diffeomorphism from this manifold to that manifold is defined on a large ball here. It contains a large ball centered at the base point there. And then I can compose that partially defined diffeomorphism with this projection map. Okay? And so I end up with a map from M into R2. And at least on a large ball centered at P, this will, or inside there, you'll see a circle fibration, just as this is a circle fibration over there. Okay, so now we can look at the structure near points of the other type. So if you have a 1-stratum point, so then you have an isometric splitting like this. And as in the 2-stratum case, you can define a projection map this time to R. However, there are kind of 2 cases to consider. So one is that the diameter of this cross-section, so we now have R across something. The first case is the diameter of the cross-section is not too large. And then I'll say that this is a slim 1-stratum point. So the motivation for this terminology is the following. So the model manifold is R across this cross-section. So if you scale that down a little bit, the cross-section has control diameter. You scale it down a little bit, you see something that looks a lot like a line. That means the manifold itself looks a lot like a line. It's kind of thin, but we're already using the word thin, so this is slim. So in this case, the cross-section will be a closed non-negatively curved orientable surface. So it's S2 or T2. And this map NP will be a fibration with S2 or T2 fibers. Okay? So at least near the base point P. Now, there's another type of point that we have to deal with in connection with the 1-stratum. So you define edge points. So a point is an edge point if this model manifold splits like this. Again, R cross something. But this, instead of having control diameter, instead it should look roughly, so formally in the pointed Gromov-Hausdorff sense, like a ray. Okay? So if the cross-section looks like a ray, then R across that looks like a half-plane. So in this case, we're looking at the model manifold looks, in the Gromov-Hausdorff sense, like a half-plane. And so does, since the model manifold is a good approximation to the manifold M, then you can say the same thing about M. That's why we call these edge points. And in this case, you have, again, a projection map to R. And if you restrict that to the right part of the manifold, you get a D2 fibration, okay, of a subset line close to the edge points. Now, finally, we have the 0-stratum points. So these have been defined kind of by the process of exclusion. So they're the points which aren't 2 stratum points or 1 stratum points or edge points. So it's kind of the junk pile that's left over. But actually, we do have some structure here because we know that for any point in the manifold, the geometry looks like the geometry of a non-negatively curved manifold. Okay? So again, by applying a compactness argument, what you get is that if you have a 0 stratum point, then you can find a scale. So R0p. So trust me, I've suppressed a very large number of parameters, so I apologize for the notation, but this is a very small fraction of what shows up in reality. So we can find some scale. It's bigger than this RP, less than a constant times RP, so that if you rescale by this thing, so again, this corresponds to taking, you can think of this as now, you first rescale by this guy. You're looking at the manifold at a certain scale. And then you blow that down in a controlled amount, and you arrive at this scale, R0p. And at that scale, the object is close to a non-negatively curved manifold, which is no better than what we had before, except you have an additional feature. So I have a superscript here because this model manifold will probably be different from the NP we considered before. So what you know is that this ball is actually diffeomorphic. The ball of radius R0p is actually diffeomorphic to this model manifold. And so this is useful because we have a classification, a topological classification of complete non-negatively curved manifolds. Okay? And finally, the manifold rescaled, viewed at this scale, is close to the metric cone. All right? So we don't have a product structure here to define the map eta p that we had before, but what we use instead is the conical structure that's visible at this scale, and that allows you to define a smooth function here, which is an approximation of the distance function from the base point p in this nearly conical space. So this is globally smooth, but it has nice behavior, particularly nice behavior in this metric annulus. It has no critical points. All right, so now the next step is to see that these local structures in the form of these eta p's for different points are actually compatible. So for instance, if you take p and q to be two stratum points, then you have eta p and eta q, and these define circle fibrations near p and q. Right? Near meaning at a scale comparable to their respective scales. Suppose you have these 2 points are actually reasonably close. So let's say the distance from p to q is at most some constant. So this symbol means a constant times the scale at p. So then the regions, the fibrid regions associated with p and q, the fibrations, are going to have overlapping domains. And in this case, the 2 maps will be compatible in the sense that eta p and eta q will be affine functions of one another up to C1 small error if you measure it in this rescaled manifold here. Okay? So you have similar compatibility holding when p and q are slim 1 stratum points or edge points, and also you have compatibility between the points with different strata. Okay? So now the last step involves gluing these kind of locally defined fibrations given by these etas. And so I'm not going to say much of anything about this. It's essentially an elementary problem, okay? But it's kind of annoyingly complicated. It's technically involved. And it's hard to appreciate this until you start to really think about it. So initially I thought it was completely trivial. But so the main complication, you could say the main complication is coming from the fact that you don't have, so when you normally want to glue 2 maps, like you want to glue 2 real valued functions, you just use a partition of unity, right? The problem here is that we have fibrations which are taking values in different targets. Okay, not even the same target. And this gives a hint of what some of the issues are. So we have a way of dealing with this. So the idea is to use these local fibrations, the etas, to define a map from the manifold into Hilbert space. So it's a little bit like in the proof of the Whitney embedding theorem. You use these functions kind of like coordinates, and from those you cook up a map into Euclidean space. And you show that this map, when you restrict it to certain parts of the manifold, behaves kind of like a rough fibration. And then there's an elementary argument that the rough fibrations of this sort can always be perturbed to become honest fibrations. And that's how we get that's how we handle the gluing issue. And a nice feature of this is that since this is constructed globally, the different types of fibrations that you see are automatically compatible with one another in the final story. And so it's, you just simply recognize that you have a graph manifold. So I'll stop there.
Any questions for Bruce?
How much did you have to add to Perelman? How many details?
Well, actually, unlike the rest of the material in his first two Richie flow preprints, there was only a statement in this case. So basically, we have to add everything. The history is a little bit confusing because, in a sense, so Perelman posted his second preprint, which it had a statement of this collapsing result with the derivative bounds, and within a month or so, Shio and Yamaguchi posted their preprint on the archive, which effectively dealt with the problem. So it became unnecessary for Perelman to write another preprint giving the proof. But actually, this kind of collapsing result, I mean, the Shio and Yamaguchi paper was based on Perelman's stability theorem, which was one of the outgrowths of his work on Alexandrov spaces that began with the paper with Barago, Gromov, and Perelman around 1990. So, I mean, he was working kind of very rapidly during that time, and he, in public lectures, stated a collapsing result of the sort that I have here, although you need some hypotheses because, well, you need something like the Shio Yamaguchi statement. In any case, so he had stated this, but he never wrote it down back then in the early 90s, so it came to Shio and Yamaguchi.
Very good. Well, let's thank Bruce again.